Let us look at proposition number 60 of book 10 of Euclid's Elements. Before we look at the proposition itself, there is a lemma. So let's look at the lemma first and then we will look at the proposition. The lemma says, if a straight line is cut into unequal parts, then the sum of the squares on the unequal parts is greater than twice the rectangle contained by the unequal parts. So what the lemma is saying is, if AB is cut into two unequal parts, AC and BC, then AC square plus BC square is greater than 2 times AC times BC. So let's prove this. Let AB be a straight line cut into unequal parts at C. And let AC be greater than BC. Because it has been cut into unequal parts, we can say AC by BC plus CD square. Now, where did this D come? D is the midpoint of AB. So we can say AC by BC plus CD square is equal to AD square. This is one of our core propositions. Now, that means if we remove CD square, AC by BC becomes less than AD square, which means if we multiply or double both the quantities, it becomes 2 times AC by BC is less than 2 times AD square. AC square plus BC square is equal to 2 times AD square plus CD square. Now, this is again based on a proposition from book 2. Now, AC square plus BC square is equal to 2 times AD square plus 2 times CD square. Now, 2 times AD square is there here. So 2 times AC by BC is less than 2 times AD square. So if I substitute this here by 2 times AC by BC, then what happens? Since this is less, I'm substituting a lesser quantity. That means AC square plus BC square becomes greater than the right hand side. So AC square plus BC square is greater than 2 times AC by BC plus 2 times AD square. And finally, if I remove this 2 times CD square, it becomes AC square plus BC square becomes much greater than 2 times AC by BC. A little bit tricky here, but think over it and you will see the logic. So that was the lemma. Now let's look at the proposition. Proposition says the square on the binomial straight line applied to a rational straight line produces as breadth the first binomial. So here, let AB be a binomial straight line divided into its terms at C with AC greater than BC. So we are applying a binomial straight line to a rational straight line. So set out DE a rational straight line. Apply a parallelogram DEFG to DE equal to AB square or square on AB. Actually, this would produce a breadth, that is DG. The proposition says that DG is going to be a first binomial straight line. So let's see how we can say that DG is a first binomial straight line. So apply a parallelogram DH equal to AC square to DE. Apply a parallelogram KL is equal to BC square to DE. Of course, we are not applying directly to DE, but we are applying it to KH, but that KH is going to be equal to DE. Now, since DL is AC square plus BC square, the remainder MF is going to be 2 times AC by BC. Bisect MG at N. So MO will be equal to NF equal to AC by BC. So basically 2 times AC by BC is MF. We have cut it into half so that each half is AC by BC. Now AC and BC are rational straight lines commensurable in square only. AC square and BC square are rational and commensurable with one another. That means AC square plus BC square is also going to be rational because AC square and BC square are rational. Now, AC square plus BC square is nothing but DL. So DL is rational. Now, if DL is rational, DM is also rational and commensurable with DE. 2 times AC by BC is equal to MF. This is going to be medial because AC and BC are rational straight lines commensurable in square only. MF is applied to ML. MF area is applied to ML, which is equal to DE, which is a rational straight line. So that means MG is rational and incommensurable in length with ML, that is DE, because this is medial and this is rational. So which means DM is incommensurable in length with MG. Why? Because DM is rational and commensurable with DE and MG is incommensurable with DE. That means they are going to be incommensurable with each other, DM and MG. So that means DM plus MG, which is DG, is a binomial because DG is a sum of two rational and commensurable in square only. Now AC by BC is the mean proportional between AC square and BC square. One of the older lemmas. MO is the mean proportional between DH and KL because AC by BC is MO and AC square is DH, BC square is KL. So which means we can write it as DH is to MO equal to MO is to KL. Now which means DK is to MN equal to MN is to KM because DK is the side of DH, the base. MN is the base of MO and Km is the base of KL. Yes, which means we can write it as dk times Km is equal to Mn square. That means dH is commensurable with KL. So which means dk is again commensurable with Km. This is again based on one of our previous propositions. Now, based on the lemma we just saw, AC square plus BC square is greater than 2 times AC by BC. AC square plus BC square is greater than 2 times AC by BC. That means DL is greater than MF, which implies DM is greater than MG. Again, based on one of our previous propositions, dk by km is equal to mn square, which is equal to the square on half of mg. See, when we say mn square, it is look at the square on mg. If you look at the square on mg, mn square, n is the midpoint. So mn square would be 1/4 of mg square. And dk is commensurable with km. So again, based on a proposition which we have seen, we can say dm square is greater than mg square by the square on a straight line commensurable with dm. dm square is greater than mg square by the square on a straight line commensurable with dm. That is a greater. So we have d anyhow is rational. We have shown that dm is rational and dm is commensurable with de. And if you look at the definition of a first binomial straight line, you will notice that dg is a first binomial straight line. That is proposition number 60 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.